Right.
Hello, everybody. Thank you for connecting. I'm Clara Rodriguez, one of the co-founders and co-chairs for this technical interest group. It is my pleasure to introduce our speaker today, Sian Evans. Sian is about to finish her PhD in the Basins Research Group at Imperial College London. She has a Master of Science in Petroleum Geoscience from the Imperial College London, sponsored by Statoil or Equinor, and also an integrated Master in Science in Earth Sciences at Oxford University. Her PhD research has focused on investigating the effects of base salt relief and intra-salt heterogeneity on salt basin evolution using seismic data and physical analog modeling, for which she was awarded a 2019 AAPG grant in aid. Sian is also very passionate about public engagement, spreading the love of salt at festivals, pubs, museums, and even stand-up comedy. Welcome, Sian, and thank you for presenting for us today.
Hi, Sean. Welcome. This is Tim. Sorry for joining a little bit late.
Thank you. Okay, so I will share my screen and then we can get started. Okay, hopefully you can see that. Okay, is that working? I'll take the silence as a yes. Okay, so the title of my talk today is a little bit of a mouthful, but hopefully even if you have no idea what I'm talking about from the title, all will become clear by the end of the talk. So the title is Taking the Pulse of Salt-Detached Gravity Gliding in the Eastern Mediterranean using Ramp Syncline Basins and Fluid Escape Pipes. So the work that I'm presenting today is basically an overview of these two papers that we've recently pre-printed, and they're currently in review. One of them, led by me, has the same title as the talk that I'm giving today. The other one, the work was led by Davide Oppo at Louisiana, and that is more on the fluid escape side of things, whereas my paper is more on the salt tectonic side of things. But there's a lot of overlap between the two papers, as you'll see in the talk. So if anything I present today kind of sparks your interest, I would encourage you to go and look at our preprints on Earth Archive, and yeah, do get in touch. We're always happy to chat about our work. Okay, so let's get stuck in. So I am going to be talking about a little case study from the Mediterranean today. So we're going to be looking at the Messinian salt, which is a bit different from some of the salt basins that we've been looking at previously in this talk series, in that it's a lot younger. So the Messinian salt in the Mediterranean is only 5 to 6 million years old, and it was deposited when the connection between the Mediterranean and the Atlantic through the Gibraltar Strait was cut off or restricted, and a large volume of salt was precipitated in many of the basins across the Mediterranean, as you can see here. So my study area is actually in the Eastern Mediterranean, so we're going to study into this corner of the map. And you can see my data set is located where these pink polygons are. So this is a 3D seismic data set on the Levant margin. And you can see this is a relatively complex area geodynamically. So we've got the subduction zone occurring to the north of the basins along the Mediterranean ridge. And the extension of that is the Latakia ridge, which actually crosses our data set to the north. We've also got a strike slip system onshore to the east through Lebanon and Israel. We've got the Eratosthenes seamount, which is a continental block that separates the Levantine and the Herodotus basins. And we've got the Nile Delta, which is prograding into the basins from the south. So there's actually a lot going on here that the salt can potentially respond to. But the area that we're looking at is a zoom in here, which is essentially a passive margin offshore Lebanon. So this is a typical cross section through the margin. And if I just add an overlay and point out some features to you, you can see this is the salt layer here. So the top salt is this nice bright amplitude reflector. The base salt, for the most part, is a nice bright amplitude reflector as well. And what's immediately obvious or quite unusual about the Messinian is this internal reflectivity, which is really well imaged in the Messinian. Because it's so young, it's so shallow, so it's very well imaged in seismic data, and it's also relatively undeformed, especially if you compare it to the kind of crazy salt structures that we were looking at in Karina's presentation a couple of weeks ago. So it's a very early stage system that we're dealing with here. And you can see the salt thins out, up dip, if you follow the salt sheet, and then eventually pinches out up onto the margin. And so we're dealing with what is essentially the early phases of gravity gliding in this system. So we've got a tilt on the base salt surface, and the overburden is essentially sliding towards the basin. So we've got this up dip zone of extension that you can see here, these salt-detached normal faults and associated salt rollers. And we also have a lot of contraction down dip, but mainly within the salt itself. And that's because there was a Syan depositional phase of deformation that created a lot of this contraction. But the Syan depositional story is actually a story for another time. In my talk, we're going to be looking at the later phase of deformation, so the gravity gliding phase, and we're going to be looking at features within the overburden. And there's actually not a lot of contraction in this data set in the overburden. Okay, so looking at the structure of the margin in the data set, you can see here the thickness distribution of the salt. So exactly as we saw in the cross section, you can see we've got thickening towards the basin, thinning up dip, and then eventually pinching out onto the margin. In the top salt map, you can see we've got that network of extensional faults, mostly basinward dipping faults in the extensional domain. And we've also got a local area of reactive rise accommodating the extension locally there. And we've got some very local buckle folds, which are close to the Latakia Ridge. So there's some restriction in the salt flow around the Latakia Ridge, which is creating this compression here. But for the most part, the distal area of the overburden is relatively undeformed here. And then in the base salt map, we're going to meet our protagonists for this talk, which is these large anticlines on the base salt surface. So you can see several of them if you look across the data set. There's a large one in the south there as well. So if I add the overlay on, I've just picked out some of the largest ones here, these large base salt anticlines. We've also got, if you can see here, let me just flick back. Hopefully you can see that there's very, very small offset faults on the base salt surface as well. So these are very small normal faults in the subsalt. They don't appear to propagate up into the Messinian interval, but they do have very small offsets at the base salt. But mostly we're going to be concentrating on the story told by these large anticlines. So this is a cross section through one of those large anticlines on the base salt surface. So these are compressional features. As we've seen, we've got a subduction zone to the north. So we are dealing with a basin that's in compression here. And they are thrust related faults. So it's not particularly well imaged, but there's a thrust fault somewhere here that's offsetting the base of salt. Some of the folds are just fault propagation folds, so you don't actually see any offset at the base salt itself. But they are all relatively large, or the ones we're going to look at are all relatively large compared to the actual thickness of the Messinian itself. And the effects that these anticlines have on the salt is essentially there's two important effects that we're going to look at in this talk. So if I add the interpretation, hopefully you can see clearly these colored horizons here. And these units are thickening in towards the anticline, dipping towards the anticline, and then onlapping onto this basal surface here that's highlighted with that dotted line. So we've got these thickening and onlapping wedges that come in towards our basal anticline. We've also got, if I just point out on the uninterpreted section, these vertical features underneath what we call a ramp syncline basin. So this thickening, these thickening wedges are characteristic of what we call the ramp syncline basin, which I'll talk about in a sec. And underneath the ramp syncline basin, we have these vertical features that extend from the top salt and detach at that onlap surface. And those are essentially fluid escape pipes. So in the first part of the talk, I'm going to deal with the story that the ramp syncline basins are telling us. And then in the latter part of the talk, I'll come back to the story associated with these fluid escape pipes. So if you're not familiar with ramp syncline basins, hopefully this video will clear up how these ramp syncline basins actually form. If I can get it to play. There we go. Okay, so what we're looking at here is a physical analog model. So this darker brown layer here is our salt analog, that's silicon. And the silicon is flowing down dip over a series of steps on the base salt surface. And as the silicon flows over these steps, it creates this local depot center adjacent to those steps. So you can see one depot center forming here, one depot center forming adjacent to this step as well. And as that depot center forms adjacent to the step, it creates accommodation space, which the synkinematic sediments then thicken into. So they thicken into the space created adjacent to the step, and then they onlap onto the strata above. So you can see the wedges coming in here, thickening, and then onlapping onto this surface. And then as the translation continues, the overburden continues to be translated over the steps. These onlaps and these thickened wedges are then translated away from those steps. So you can now see some of the early layers that were deposited, the synkinematic sediments, are being moved away from where they originated at the base salt step. So we've got one ramp syncline basin here forming adjacent to this step, another ramp syncline basin forming here adjacent to this step. And this is essentially a characteristic growth strata associated with the formation of these ramp syncline basins. So this is, I forgot to mention, this is actually a CT scan. So it's slightly fuzzy quality, which I apologize for, but hopefully you can see quite nicely the development of these thickening and onlapping wedges, which are part of the ramp syncline basin. Okay, so that's what we're looking at here. We're looking at a record of salt flow and overburden translation over these base salt anticlines, and then deposited synkinematic sediments which have infilled the accommodation related to that salt flow. So that's really useful when we're looking at gravity gliding systems, because it means we can quantify the amount of translation that has occurred over this base salt anticline. We know that this onlap originated above the anticline at what we call the ramp syncline basin hinge, or the RSB hinge. So the horizontal distance from that very first onlap to the present day RSB hinge gives us a magnitude of translation, a total magnitude of translation that has occurred over this anticline. And if we look across the margin now, so we were looking at this ramp syncline basin, we've actually got 8 of these ramp syncline basins developed adjacent to different anticlines on the base salt surface. And so let's look at the internal geometry of this ramp syncline basin a little bit more. So this is a depth map of the basal onlap surface, and you can see we get the greatest subsidence in the center of the anticline, as you might expect, and then we've got these gently dipping sides. And then if we map one of those internal units within the ramp syncline basin, we can see that pattern of thickening as it comes in and then onlapping onto that basal surface. So we can map out the thickest part of the succession of each of those units. And if we map the thickest part of those units within the ramp syncline basin, we get a really nice image of the migration of the depot center away, well, not the migration of the depot center, migration of the strata away from the ramp, the basal anticline. So this red one here, that's our present day depot center in red, adjacent to the basal anticline. And then they get older and older and older as you move away from the basal anticline. And this light pink one here, that's our oldest paleo depot center, if you like. So that gives us a pretty good constraint on the direction of translation in this system over this particular anticline. And we can do exactly the same thing with the onlaps as well. So we can trace the onlaps associated with each of those horizons, and then we can map them out and look at them in plan view. So we've got the present day RSB hinge, which is in red here, and then they get deeper and deeper and deeper onlaps, older and older and older, until that light pink onlap that was furthest away from our present day RSB hinge. So that distance from the present day RSB hinge to the oldest onlap is again giving us the total translation that's occurred over this anticline. And you can also see some of the pipes that have been mapped in this, but we'll come back to the pipe story a bit later on. So what we can also do is now calibrate or correlate the ages of these horizons between different ramp syncline basins. So for example, we can map this light pink horizon out across the basin, and then we can look at where it onlaps in each of these different ramp syncline basins, which means we then have the same age onlap mapped in light pink for each of these ramp syncline basins. So all of these colored lines are the same age in every ramp syncline basin here. That's what these series of colored lines are showing here. Hopefully you can see those okay. So what that means is now not just being able to compare total magnitudes of translation for the ramp syncline basins, but also being able to look at incremental translations. So what we mean by that is we can say that between the deposition of the light pink horizon and the deposition of this dark pink horizon, this much translation occurred during that time interval, the horizontal distance between those two onlaps. We can say exactly the same then for the next time interval between the deposition of the dark pink and the purple horizons and measure that translation, and so on and so forth up until the most recent translation estimate. So what does that look like? Well, let's have a look at these graphs. So this light pink onlap, that's our oldest onlap. So that's essentially our total translation for each of these ramp syncline basins. And you can see we've actually got quite a large spread in the total magnitude of the translations for these ramp syncline basins. So we've got a minimum of 5 kilometers of translation for RSB2, and that goes all the way up to about 7 kilometers of translation recorded by RSB6. So there is a bit of, obviously there is a bit of error associated with these measurements. The error can be tens of meters, but it certainly can't account for multiple kilometers difference in the magnitudes of translation. So we think this is real disparity in the data that we're looking at. And if we then look at the incremental translations, so now we're looking at during the time interval between these two horizons being deposited, how much translation does each of those ramp syncline basins record, and then the next time interval and the next time interval up until the present day. And again, we see the same variation in the magnitudes of translation recorded along the margin. So there is clearly some difference in the rate of translation that's occurring along the margin. And the rate of translation varies both temporally and spatially as well. So you can see if we go from one time interval to the next, it's not always the same ramp syncline basin that's going faster and the same ones that are going slower. They actually switch around so that at some parts of the margin, the overburden can be translating faster during one time interval, and then that will slow down and another part of the margin will move faster during the next time interval. So what could possibly be controlling these lateral spatial and temporal variations in the rate of translation along the margin? Well, we're going to start by considering the heights of the anticlines and if the height of the anticline has anything to do with it. So not all the anticlines that we're looking at have the same height. Some of them are a lot larger than others. So we've got some anticlines. So the anticlines here are represented by these blue triangles. And the maximum height of the anticline here you can see is just over 800 milliseconds. And then the very smallest anticline that we've got is only just over 200 milliseconds. So there's a large difference in the heights of these anticlines along the margin. And you would expect that a larger anticline would have a greater effect on the salt flow. A larger anticline is probably going to impede the salt flow much more than a very small anticline would. But there's a more useful way that we can think about how much an anticline is impeding the salt flow. So we've got this base salt anticline here, and we've got the salt which wants to flow down dip. So it wants to flow over this anticline and then continue heading towards the basin. Same with the overburden, that's translating. And what we've got here is a large thickness of salt up dip and a relatively small thickness of salt over the anticline. So it's going to be quite difficult for this thick salt up dip to squeeze through that relatively small gap so that it can continue flowing down dip. So that's what we've termed a salt flux imbalance, or it's a proxy for how much we think the salt flow is affected by the base salt anticline, the salt flux imbalance. So if there's a large difference between the thickness of the salt up dip and the thickness of the salt over the anticline, that's a large salt flux imbalance. If there's only a small difference between the thickness of the salt up dip and the thickness of the salt over the anticline, that's a small salt flux imbalance. The salt is probably not being impeded that much by the anticline. So if we look at our graph, these vertical lines are then representing the magnitude of that salt flux imbalance. So a longer line here means that there's quite a large difference between the up dip salt thickness and the thickness over the anticline. And a small vertical line here means there's a relatively small difference between the thickness of the salt up dip and thickness of the salt over the anticline. So large anticlines generally associated with a larger salt flux imbalance, as you'd expect, but not always. There's some exceptions to this. So why might that be important? Well, it's because we see quite a strong correlation here between the magnitude of the salt flux imbalance and the absolute average deviation for these ramp syncline basins. So if I just go back to explain what I mean by that, oh yeah, this graph. What we've got here is not just the magnitude of translation plotted from each of those ramp syncline basins, but we've also calculated an average. So this bar at the end in gray, that's our average translation during this time interval. So the gray one in each of these cases represents the average during that time interval. And then we can calculate how much the magnitude of translation recorded by the ramp syncline basin deviates from that average. So if we go back to the graph, a large absolute average deviation means that these ramp syncline basins are showing much more extremes, that they're going much faster and much slower than the average at certain time, well, during every time interval. Whereas these ramp syncline basins with a small salt flux imbalance tend to be going at a more consistent rate that is close to the average over time. So to understand why we see this relationship between the large salt flux imbalance causing these extremes, we need to consider the mechanics of the system. So we've made this very simple schematic to kind of illustrate what we think might be going on here. So starting with a completely gravitationally stable system, we've got an anticline on the base salt that's then been buried by this pink salt. And then we've got a very thin pre-kinematic unit deposited on top of that. And you can see in this case, there's a large difference between the thickness of the salt up dip and the space available for the salt to flow over that anticline. So we've got a large salt flux imbalance. So when we tilt the margin and we tilt the base salt, we induce this gravitational instability. So now the salt and the overburden want to start moving down dip. They're gravitationally unstable. But what happens is, because the salt flow is being impeded by this anticline, pressure starts to build up on this up dip side. So the salt just physically can't get over this anticline fast enough, and pressure starts to build up here. Meanwhile, the salt down dip is able to pull away merrily. So what we start to see is a pressure difference building up across the anticline, where we've got high pressure here and low pressure on the other side of the anticline. And so we see here in this first phase, we've got pressure difference increasing. And because the pressure difference across the anticline is increasing, that means that the velocity of the salt starts to increase as well, because you're increasing the stress that's acting on the salt, and salt responds to stress. Essentially here, because we're dealing with quite low strain rates, the salt is behaving as a Newtonian fluid, where stress and strain rate are essentially proportional to one another. So as you increase the stress on the salt responds by flowing faster. So we then see an increase in the velocity as well, corresponding to this increase in pressure. What happens in the next phase then is that now, because the salt is flowing faster across the anticline, that starts to reduce the pressure difference across the anticline. So the pressure difference then starts to drop off because we've got increased velocity over the anticline, which is releasing the pressure difference. And then, of course, because our pressure difference is dropping, the stress acting on the salt is also dropping, and consequently the velocity of the salt will also then decline. It's got less stress acting on it. So ultimately then what we end up with is these cyclical phases of faster and slower salt flow as this pressure builds up and then is released and then builds up again and then is released. So we end up with cyclical phases of faster and slower salt flow and faster and slower translation across this anticline. On the other hand, where we've got a very small anticline in this case, so now we've got a small salt flux imbalance, there's not much difference between the salt thickness up dip and the salt thickness over the anticline. So the salt is not as impeded here by the anticline itself. So it's able to get over the anticline much more easily. It doesn't need to build up as much pressure up dip, and whatever pressure does build up here is released very easily by small increases in the velocity. So we get here much less variation in the rate of the salt flow over time and the rate of translation. Essentially, the overburden is able to translate at a much more consistent rate in this case. Whereas here, where we've got a large salt flux imbalance, we're seeing more extremes of faster and slower rates of flow. So we think, because we see this correlation here between the average deviation and the salt flux imbalance, that this is actually a really important control on how fast the salt and the overburden are able to flow over these anticlines. And this is what we call cyclical pulsing of the salt flow, essentially. So if you noticed in my title, I included the word pulse, which sounds a bit weird. It's actually a play on words because we talk in the paper about these cyclical pulses of salt flow. But there is also another control that we need to consider that will affect how fast our overburden is able to translate, and that is the brittle mechanics of the overburden itself. So you remember right at the start, I showed those extensional faults in the up-dip domain. So those extensional faults are essentially allowing the overburden to pull forwards because the overburden is a brittle sheet. But exactly how much those brittle faults control the translation of the overburden depends on whether we're dealing with an elastic deformation or a plastic deformation. So if we start with an undeformed sheet, as we have here, so just a uniform sheet deposited, we then tilt the margin so that overburden is now gravitationally unstable and it starts to pull forwards. There's a certain amount of elastic strain that can be accommodated in the overburden as it pulls forwards. And then if we have an elastically deforming sheet, the overburden then can't pull forward any more than that until we get brittle failure in the up-dip domain, which allows the down-dip end of that sheet to then pull forward. And then as that fault ruptures, that will increase the strain in the neighboring segment, and we then get another brittle failure, allows more of the front end of the sheet to pull forward. On the other hand, if we have an overburden that's deforming plastically, it means that the overburden can deform at constant stress. So we get the down dip end of the overburden is just pulling away merrily at its own rate. And the brittle faults in the up dip domain just form as and when they reach the critical stress required for brittle failure. In actual fact, in nature, because this is always the case when we have two end member models, in nature, we think the overburden is deforming as an elastoplastic sheet. So it's always a combination of two end member models. So it's a hybrid of these two processes acting. And essentially what that means is that the overburden, the faults in the up dip domain do exert some control on the rate at which the overburden down dip is able to pull away. So that's another thing that's going to be affecting the rate at which our overburden is able to move over those basal anticlines. So we think it's a combination, an interplay of these two processes of this cyclical pulsing of the salt flow and also the overburden mechanics and the brittle mechanics, and when we get slip and displacement on these faults in the up-dip domain. And both of those processes are going to be controlling this spatial and temporal variability in the rates of translation along the margin. So that's basically the end of the ramp syncline basin side of the story. And we're now going to talk a little bit about the fluid escape pipes and what the fluid escape pipes tell us. So you can see here again, we're dealing with these fluid escape pipes that extend from the top salt to the basal onlap surface of the ramp syncline basin. And when we look at these in plan view, we can see these are trails of pock marks that lead away from an emission point above the anticline. So these trails of pock marks were first recognized by Joe Cartwright's group in Oxford, and they wrote a couple of papers about these trails of pipes. And we have a lot of these pipe trails in our data set. So they're essentially showing, well, actually I have a nice schematic for this coming up next. They're essentially showing how these pipes break through from the crest of the anticline, and then they are translated away from the anticline and into the ramp syncline basins. So we have a number of these fluid escape pipe trails in our data set. In fact, most of the anticlines that we're dealing with in our data set have pipe trails associated with them. And there is a relationship between the age of the pipes and the ramp syncline basins. So in this schematic here, to show it very simply, you can see the fluid escape pipe forms vertically above the crest of the anticline. The pipe is then translated into the ramp syncline basin, and it's buried by the synkinematic strata here. It continues to be translated and it's buried again by the next sheet. So the age of the pipe is essentially the same as the age of the horizon that it meets at the base of the ramp syncline basin here. So you can see here a new pipe again has formed vertically above the crest, and then that pipe is then translated again into the ramp syncline basin. So each of these pipes are the same age as that horizon that they meet at the base of the ramp syncline basin. And that's a useful way of dating the relative ages of the pipes in these different trails. So why might that be useful? Well, it might tell us something else about how the salt is deforming. If we look at the pipe trails associated with the southernmost anticline here, we've got a zoom in here, and we've got a lot of these adjacent pipe trails. We might be tempted to say that all of the pipes, the first pipe in each trail is approximately the same age, and therefore we infer some kind of deformation front, meaning that we've got a faster flow of salt in the center here, which has translated these pipes further and these pipes not so much. So that would mean that we get quite drastic changes in the rate of salt flow, even across relatively small length scales. So this pipe is only about 8 kilometers long. However, if we use the ramp syncline basin horizons to date the relative ages of these pipes, so now I've colored the pipes by their age, constrained by the ramp syncline basin horizons, we can actually see that those first pipes in those trails are not the same age. And in fact, 1.5 kilometers of translation occurred between the first pipe in this trail and the first pipe in this trail. So even though those pipes are roughly the same age, they're not exactly the same age. And because the translation over the anticline is continuous, there is actually a difference in how much those pipes have been translated. And I've also put on top of this the on-lap traces for this ramp syncline basin, because these on-lap traces are essentially showing that we don't get any extreme variations in velocity across this anticline. If we did, we'd expect these on-laps to be deformed in some way We might end up with some wiggly patterns depending on where the salt is moving faster or slower as these onlaps are translated away from the anticline. But we don't see that. You can see that most of these onlaps, these colored lines, they're basically parallel to the anticline from which they originate. So it means that along the length of this anticline, we're not seeing any drastic changes in the rate of salt flow. We are, however, seeing changes in the rates of salt flow on a more margin scale. So between different ramp syncline basins on the scale of 100 kilometers rather than on the scale of 10 kilometers. We can also use that, the age constraints for something else. So this is all of the pipe trails that we see in the data set, just plotted by their distance from their emission point. So we've got distance from the emission point here at 0, and then each pipe plotted with its distance away from the crest of the anticline, essentially. But if we're looking for trends in fluid migration and fluid escape in the basin, it's not particularly useful to look for trends just based on distance. We want to be able to compare relative ages of the pipes in this trail over here to the pipes in this trail over here, for example. So if we replot this, and now using the age constraints imposed by those ramp syncline basins, replot the pipes so that we're now looking at age on the x-axis rather than just distance, and we can start to pick out some trends here. So a lot of these pipe trails, well, they're all showing very different trends. You can see in a couple of them, you could convince yourself that there is a pause in fluid escape here. Also this one where you see very, very continuous emission and then a pause and then you get continuous emission again. So those two are showing quite similar trends. But there is actually quite a lot of difference between the different pipe trails and the different anticlines. Some of them don't even start until very, very late. So this one starts a lot later than the others. And the data is quite sporadic. When we first looked at this, we tried to correlate the pipe trails or the patterns with the pipe trails with faster or slower phases of translation based on the ramp syncline basins. So we thought if the overburden is translating faster over the anticline, maybe those pipe trails would be more widely spaced, and maybe when the overburden is translating slower, those pipes would be more closely spaced. But we didn't really see a correlation with the salt tectonics. So there is an independent control on the charging and the emission of these anticlines that doesn't really correspond to rates of salt flow and rates of overburden translation. It's likely more related to the geometry of the trap, the pressure building up in the anticline, the stress that is needed for it to be able to hydrofracture through that salt layer and to be able to penetrate up through the overburden. So there's an independent control going on the charging and the fluid escape that seems to be independent of the salt tectonic system here. What is interesting though is that we tend to see a lot of these pipe trails start around 1.8 million years. So this is basically the only solid age constraint that we have in this basin. The rest we've had to do dealing with relative ages and relative rates because we don't have any other hard age constraints within the overburden. But we have one age constraint, which is this 1.8 million year horizon. And a lot of the pipe trails do start to, or appear to start to initiate around that time. So why, oh, I should also say, actually, quite important, that this is around the same age as our first onlap in the ramp syncline basin. So essentially, this is also the age that we initiate ramp syncline basin development and essentially initiate gravity gliding on the margin. So around the same time that gravity gliding initiates on this margin and translation initiates, we start to see the initial expulsion of these fluid escape pipes. So why might we see a correlation between the start of gravity gliding and the start of fluid emission in the basin? Well, we have a theory, and that's to do with the tilting of the margin. So we can see if we just look at the flooding after the Messinian salinity crisis, the deposition of the salt layer, and very little fluid migration within the basin. So we're not going to be building up much pressure or charging these traps very much during this initial phase. However, we think around 1.8 million years ago, there is an uplift event. So the Levant margin was uplifted. That would have tilted the base salt units. That tilting would have then initiated fluid migration from the deep basin, traveling up to the basin margins, then charging these anticlines at the basin margins and initiating the first fluid escape. At the same time, that tilting would also make the overburden gravitationally unstable and therefore initiate gravity gliding at the same time. So the tilting of the margin can be responsible for the enhanced fluid migration and therefore enhanced charging of these anticlines, and also be responsible for the initiation of gravitational instability and gravity gliding on the margin as well. So this does imply that we do have good lateral connectivity then from the deep basin to the basin margins, and we must have a pretty good reservoir or carrier bed to be transporting these fluids up from the deep basin to the basin margins. And the final thing I want to mention, and then I will wrap up my talk, is also coming back to these subsalt faults that I mentioned right at the start, if you remember. We've got a series of these small subsalt faults. They are very, very small throws, but we think they may have an effect on the pressure within the anticlines. So it's kind of strange if you think about it, that one anticline, and essentially one trap structure, would be associated with multiple trails of fluid escape pipes. So we're looking at this anticline here for reference, the southernmost anticline. Because we think if there is, if this was all a single trap structure and the pressure was connected, the fluid escape would occur from the weakest point at that anticline, and that would then reduce the pressure in the whole trap, and therefore you wouldn't be getting adjacent fluid escape in multiple locations along that anticline. So it's kind of indicating that you can build up pressure independently at different points along this anticline. So these very, very, very small subsalt faults that we were looking at, and you can see them if you look in the seismic section here, very, very small offsets in the subsalt, we think they may actually be sealing and therefore able to compartmentalize the reservoir within these anticlines and allow pressure to build up independently in different segments of this anticline. So that's interesting. And yes, I think that's all I wanted to say about that. And that was the final part of the talk. So just to wrap up, we've got a series of very well-developed ramp syncline basins across the Levant margin offshore Lebanon, associated with these large anticlines on the basalt surface. The ramp syncline basins seem to be recording spatial and temporal variability in the rate of translation along the margin. And we think this variability in the rate of translation is controlled by two things. One of those is the cyclical pulsing to do with the pressure buildup and release over the anticlines, and the other control to do with the overburden mechanics and the faulting in the updip domain. We've also got a series of fluid escape trails that tell us that we've got quite a lot of fluid migration and continuous recharging of these trap structures on the base salt. And they indicate that we've got good lateral connectivity from the deep basin as well. Okay, and yeah, that is pretty much all I want to say there. So I kind of said it at the beginning, but I'll say it again now. All of this work and more detail on this work that we've been doing, you can find in these two preprints on Earth Archive. And if you do want to check those out, yeah, get in touch with us and we can chat about it if you have any other questions. And I'll also take some questions now, obviously. Thank you. And I will stop sharing. Okay.
Thank you, Sian.
Thanks. So do we have some questions?
We do. We're going to see if Leo can do it.
Yes,
That's great.
Rochelle, I think someone needs to authorize my video so I can.
Oh,
Okay. I made you a co-host, Leo.
Okay, there you go. Thank you, Sian. Amazing stuff as usual. I'm really glad to see the talk and now the wrapping up of all the work and your PhD. So yeah, thanks for giving the presentation. Congratulations again. So yeah, let me start with the Q&A question. So from Carlo Giraldo, hi, why using two-way time seismic lines instead of depth converted? Very interesting presentation.
yes, yeah. So ideally, we would want to do this with obviously depth converted seismic, but we were given the two-way time, and we think because we're dealing mostly with horizontal measurements here, that there's not going to be a big effect if we depth converted the seismic. I mean, we know that those anticlines are real and not velocity pull-ups because the salt is much thinner over the top of the anticlines than it is adjacent to it. So they're definitely not just pull-up artifacts or anything like that. But there would, yeah, we could make more precise measurements on the heights of the anticlines, for example, if we did the depth conversion. But ultimately, yeah, I think most of the measurements we're making wouldn't be affected drastically by, yeah, the depth conversion. But we would, yeah, if we had it, we would.
Yeah, I know. I mean, yeah, I completely agree. I don't think that will really make a huge difference in your analysis anyways. But yeah, it's an interesting point. So the second question from Malcolm Francis, is there evidence of strike slip movement within the basalt anticlines?
Within the basalt anticlines, not that we can tell. Like nothing is like, there's no big like offset of the anticlines or anything like that. And the faults in the subsalt do just appear to have very small normal offsets on the basalt surface. So there was a paper on those faults, or at least a paper that talks about these faults by Ramadan Galaini. So they think that they are, yeah, they are due to an anisotropic stress field in the subsalt, essentially.
Right. Okay.
But they are mostly formed pre-salt and maybe during the deposition, the very early deposition of those first Messinian layers, the timing of those faults.
Right. Yeah. Okay. Well, actually, I could use like a hook for these questions. And do you see any evidence of strike slip or rotation, or something that accommodates, you know, the offset between different Syncline basins along strike? Or
yeah. So in our case, actually, no. We've got some channels that we can identify on the top salt surface that we can identify on the bearing maps. The channels, then they don't appear to be offset, so there's no obvious faults that we can pick out in the overburden that may be accommodating those differential rates of translation, no offset on those channels on the top salt surface. So we think that those differential rates are mainly accommodated by just elastic strain and stretching of the overburden. But we do, offshore Israel, they have identified a lot of strike slip faults in the overburden there. So there definitely is in the basin at large, just not in our portion of the margin that we're looking at.
All right. Okay. Yeah. Thank you. That's a good point. So the second one, well, the third one from Remy Galaini. I think you just mentioned him. So a coincidence. So good theory about fluid accumulations leading to the development of pipes. However, drilling showed no reservoir units and no accumulations at all on some of these anticlines you showed. So if there is no gas accumulations, where did these fluids come from? Are they truly HT or quite intriguing?
Yeah, so the reservoir conundrum is one we were discussing recently, actually, because the most recent well that they've just drilled offshore Lebanon, the Byblos well, I think that's the name of it, yeah, didn't find any reservoir in one of those anticlines. They did drill right into the kind of edge of one of those anticlines that we showed. and there were gas shows, as far as we understand, but yeah, apparently no reservoir unit. So we kind of, yeah, we're playing with ideas a little bit about how we migrate the fluids through the basin, but there's not a lot of good constraints on the distribution of reservoirs in the subsalt, as we understand it. But clearly, the evidence is there. The pipes are forming, and they're forming continuously. So somehow we are managing to charge and recharge those traps continuously. But yeah, how we transport those fluids and the distribution of those reservoirs is a bit, yeah, debatable.
Yeah, it's I agree with Remy. It's quite intriguing. What's the origin of these fluids? Yeah.
I don't have a concrete answer, but it's interesting.
I think it's something for another PhD or another project.
Yeah.
You already have too much.
Exactly. Yeah. That's someone else's problem.
I agree. Yeah. So the next one from Frank Pugh. Very nice talk. Sian, have you looked into the lubrication theory from the engineering literature, where there is extensive literature that has analyzed movement of viscous fluids, lubricating oil in their case, over a surface with topography, engine parts in their case. They have models for the flow and the pressure variations. So basically, have you looked into that or include that in your work?
No, but yeah, it sounds like I need to read more into the engineering side of it. Yeah, what we've got at the moment is pretty much a conceptual model, and it's based on what we know about the behavior of salt in terms of it being a Newtonian fluid at low strain rates, and the mechanics of the system in that sense. But yeah, if there are some engineering papers that I've written about a similar mechanism, I would definitely be keen to read. Please send them.
Me too. I would like to read that. Next one, it's okay, Torsten Handerbo Hansen. I hope I didn't pronounce it super wrong. So great talk, super interesting stuff. Two questions basically. What allows the escaping fluids to penetrate the Messinian salts above the anticlines? Which sediment types overlie the anticlines? They seem to deform in a very ductile manner in response to extension, judging from the seismics.
Okay, so the first one was on how the fluids are actually escaping from the anticline. So we've kind of invoked a hydrofracturing mechanism. So we think there's some sort of critical stress required to basically brittle fracture the overlying salt and the overburden. And so you'd have to build up a really large pressure in those anticlines. But it is really unusual because obviously, usually we think of salt as being an amazing seal. You know, it's like, and especially salt that thick as well. And it's relatively thick over some of those anticlines. And yet we're still managing to see these fluid escape pipes forming over the rest of these anticlines. So it's a very good question. And it kind of, it bucks what we think we know about the impermeable properties of salt. But all I can say about that is there obviously is a critical stress required to fracture that salt. And we think, yeah, these anticlines must be large enough and permeable enough to build up enough buoyancy that's creating enough stress to hydrofracture through that. There is another theory, and that's if there's any potential like dissolution above the crest of the anticline, and it's creating some failure in that sense or managing to escape in that sense. But the fact that these pipes are so vertical and they're always vertical, we think maybe even if there is a bit of dissolution just above the crest of the anticline, it gets to a certain point where that vertical penetration has to be hydrofractured. Otherwise, if it was just worming its way through, we wouldn't see such a linear, you know, shoot through of those pipes. But yeah.
Okay. Yeah. I mean, the other thing, like, if I can just maybe make my theory is, it could be that you have a highly sheared salt in the down dip side of the anticline, and sometimes it's very thin relative to the other area. So maybe they have extremely thinned salt, attenuated salt, and salt in your area is very heterogeneous as well. So you could have most of the halides evacuated and have mostly the intrasalt layers, you know, I don't know. It's just a sort of random thought, but
Yeah,
it could be.
It could, because I mean, yeah, we don't see any of that nice reflectivity within the salt that's over the anticlines, and it looks like in the up dip domain it's still quite halite rich, even further up dip than the anticlines. So we think there's definitely halite in there, but it may, it may be that it's weakened partly because the halite has moved out and it's a lot of the intrasalt layers left. But yeah.
Or highly deformed, and maybe you don't see that much.
Yeah, the whole thing is definitely highly sheared and highly deformed. So yeah, that might have an effect on weakening it.
Cool. Yeah. So it's still this the second part of the question. So what sediments overlie the anticlines because they seem to deform in a very ductile manner? Contorsing.
I presume that they mean the sediments in the overburden. Yeah. So. Yeah, it is interesting. There's a certain amount of flexure required for the overburden as it moves over that anticline to bend in the way that it does. And again, I think that's coming back to the kind of elastic strain aspect of this. So to a certain extent, yeah, the overburden can bend and it can flex and it can accommodate that kind of deformation. And because we're dealing with what's relatively shallow overburden here, yeah, I think it can accommodate more elastic strain than if we were dealing with some very, very old and very, very lithified salt overburden. So yeah, to a certain extent, it's able to accommodate those kind of bends and stretching.
Okay, I'm not sure if I froze. I think, yeah, my connection
a little
streamed a bit. Yeah, sorry. I'm back now. Okay, I'm gonna move to the chat because I realize there's also a lot of comments in the chat. But first, I wanna ask you, because you're already going over time, so are you still okay to go have a few more questions? Or?
Yeah, we can do a few more for sure, yeah.
There is a lot of interest, so you may be here for another whole hour, so get ready.
I mean,
right,
yeah.
Sorry.
No, it's okay. I mean, any questions that I don't answer here, I can happily answer by email. And yeah, I think for previous talks we've done that as well for this series.
Cool. So yeah, let's move on. So just some comments. So from Unger Zoltan, hi, I could manage to join the session. Happy face. From what's the second one? I can't read the name. It's Frastio Delogocos. I'm so sorry, my pronunciation may be horrible for this. This is fantastic. Another one from Carlos Giraldo, very nice. Another one from Clara about the questions, and so the other one is a question from Kenneth Peterson. What may be the source of the fluids? I think that kind of goes back to Remy's question. What may be the source of fluids creating the escape pipes? Yeah, so I think you kind of covered there already.
Touched on that a little bit, and that is still, a kind of ongoing debate where the actual source of the fluids.
Okay, so the next question is from Mark Rowe. So Sian, what is happening in 3D between your pockets of ramps Syncline basins? Your own lap lines were broadly parallel in each area. Do you see discrete tear faults between offset ramps Syncline basins? Do you see any record of translation, etc.?
Yeah, I think we kind of touched on that a little bit as well with answering the question about the strike slip faults in the overburden.
Yeah.
So in this area, we actually don't see pair faults between the different ramp Syncline basins, and we think that those differential rates are accommodated by elastic strain. So we've got a relatively weak overburden here, or at least an overburden that can accommodate quite a significant amount of elastic strain. But yeah, we do see a lot of those strike slip faults to the south in the offshore Israel region, which is interesting. What was there a second part of the question?
Do you see any record of translation? I think the ramp Syncline basins would be the
the pipes and the ramp Syncline basins are the record of translation. Other than that, no, we don't see we don't see offset channels or anything like that. So.
Yeah, I mean, I think it makes a lot of sense that your overburden is relatively weak. You have a very shallow, very thin overburden. It's quite deep water, so it may be very shaly, very weak.
Yeah.
I'm going to move on to the next question. I think there's a lot to debate about that, but we need to move on. So the next one from Eric Scott. What is the relative difference between rate of salt movement over the basalt anticline and the rate of development and establishment of the fluidscape pipes?
Yeah.
Also, what is the mechanism that provides a fluid pathway through the salts? I think we touched on already, to create the escape pipes in the overburden.
Yeah, so I think the last question we touched on already, where we think it's a hydrofracturing mechanism, but there may be other things like dissolution coming into play as well, but we think it's dominantly hydrofracturing in our model. The first part, so what is the relative difference between the rate of salt movement over the basal anticline and the rate of development establishment of fluid escape pipes? So the overall rate of salt movement is, it varies. It's from like 2 to 5 millimeters per year when we calculate that based on the 1.8 million year age marker that we have in the basin. So there's a few millimeters difference in the rates of translation. And in the rate of the development and establishment of fluid escape pipes, that's kind of difficult for us to constrain because we only have that one age marker in the overburden. We can only really look at anything relative apart from that. So we can't really say much for the development and establishment, or the rate of development and establishment of the fluid escape pipes. But yeah, like I said, I kind of mentioned in the talk that we don't really see a correlation between, or we don't really see a control of the rates of salt movement and overburden translation controlling the spacing and the development of those pipes. So there's some kind of independent control there to do with the charging of the trap and the critical stress required for hydrofracturing that's controlling the development and establishment of those pipes.
Okay, cool. Let's maybe go back to the Q&A. So kind of see. Okay, so the next question from Ehab Aboutiev. Does salt diapies hold hydrocarbons? Their movements, does salt diapies hold hydrocarbons? Their movement is due to tectonic activity. I think, I'm not sure if this is a sort of generic question or related to your area, but I don't know if you care to comment.
Yeah, and I mean, we only have some very local reactive diapir development in our basin. We're mainly seeing the traps being these subsalt anticlines, so not actually the diapirs acting as traps in this case, but just those anticlines on the basalt surface acting as the traps. I'm not sure if that answers the question.
Yeah, I mean, it's okay. I think we can move on to next questions. I have a lot of questions. So a comment from Malcolm Francis. I would have a careful look. This part of the med is complex as you are on the outside of the Lebanese restraining bands. Mm-hmm. So there may be some other factors playing a role in salt movement. I'm not sure if that's what.
Okay, yeah. I mean, if you have another idea for what can be controlling these rates of overburden translation, do get in touch. I'd be very interested to hear any other theories.
Another one from Carlos Giraldo. So is it possible to trap oil inside Messinian turbidites? I understand there would be an analog of Prinos fields in Greece, where sacs and turbidites are interbedded. Thanks again and congrats.
Yeah, interesting question. I'm not sure on that actually. I guess in theory, yes, because I mean, we're getting some fluid migration through the basin. How you then transfer those fluids into the intrasalt layers might be an interesting problem, but there are some places where it's almost welded, in the up-dip domain at least. In the down-dip domain, that would be more difficult. So I guess in theory possible, but we haven't really seen anywhere where that could be a mechanism. Also, those intrasalt layers are mostly clay rich as well, or the ones that have been drilled, although there's not a very, very good constraints on the distribution of those lithologies in the intrasalt layers, but they do seem to be mostly clay rich. So yeah, maybe not very good carrier beds for fluid migration.
Yeah, that's actually very interesting. So there are turbidites within the Messinian evaporite sequence somewhere in the basin.
Potentially,
Okay.
yeah.
But they haven't been proven yet.
Not to my knowledge, no.
Okay, right. Yeah, that's interesting actually.
Yeah, but yeah, those layers do appear to be plastic, and where they've been drilled, they are clay rich.
Yeah.
So it's not crazy to think that there's some sand rich pockets and turbidites in
Could
there
be.
as well.
Yeah. Cool. The next one from James. Is there any chance the salt will go around the anticlines? I think. Yeah, that's also another kind of question. I think we chatted about that already. It's the timing of the anticlines. I think there's a bit of reactivation post salt, I guess, from what I saw from your talk.
Yeah.
So yeah.
The first part of the question about whether the salt moves around the anticlines, because that's interesting as well. So yeah, but obviously we are dealing with a 3D system here. So when that salt is impeded by the anticline, there is probably an element of the fact it will be pushed out laterally and go around the edges of the anticline as well. So our proxy for salt flux imbalance is kind of based on this idea of a 2D model, but there probably is an element of salt flowing in and out of the plane as well. But it seems to be, yeah, I mean, not all the salt is going to be able to flow around the edges. So there is some pressure buildup on the updip sides of those anticlines as well.
Sure, yeah. Cool. Another one from Malcolm Francis.
Yeah. Sorry, and then your second question was on the timing of the anticlines.
Yeah.
So we think the anticlines grew mostly pre-Messinian, so pre-deposition of the salt unit, but yeah, we can't rule out the possibility that there has been later growth of those anticlines. So we don't see that there's any major uplift event within the overburden. So we don't see that the overburden has been pushed up by one of these anticlines suddenly growing out of nowhere. But maybe, you know, if there was some reactivation of those folds and they grew slightly, that growth could be accommodated by thinning of the salt over the anticline. So it's a little bit cryptic. So there may have been some late reactivation of those folds, but we know that they at least existed pre-Messinian as well.
Yeah, I agree. Well, I think if there was any sort of reactivation, you don't see any evidence of that in the overburden, do you? You'd be pretty much cryptic within the salt, or there may be some hidden evidence somewhere. But yeah, I agree. So a few comments from Malcolm again. I kind of think I lost. Oh yeah, there you go. Strike slip becomes extension when you cross salt layers. Extension might let fluid escape each time the basement moves. So that may pretty much answering his previous comments and saying that I think, you know, the fluid escape may be related to strike slip and extension in the base salts. I think the pre-salts. And then he says, great talk, very interesting research. So I don't know if you want to comment, or we can also move on to the next one.
Yeah, I think, if the comment was just that maybe the fluids are using those faults in the subsol as fluid pathways, then yeah, I agree. Yeah.
I think so. Yeah. So the last one from the KA is from Nicholas Orich. Hi, Sian, nice work. Congratulations. Oh no, I actually jumped. I'll go back. Congratulations. Do you think there is an effect of the internal structure of the salt in the salt flux imbalance, like less mobile layers like anhydrite affecting the flow above the basal anticline?
Yeah, so we did consider that as well, but there's not a lot in the terms of internal reflectivity that we can actually see over those basal anticlines and around those basal anticlines. A lot of that internal reflectivity is much better imaged in the down dip domain. And a lot of the internal layers, they also truncate against the basalt surface as they move towards the updip domain. That doesn't mean that there isn't intrasalt heterogeneity over the anticlines though. And that also may be having an effect, but it's much more cryptic. It's kind of difficult for us to say with any certainty because we can't see it there and we don't have any constraints from drilling what kind of effect those potential intrasalt heterogeneity maybe have on the salt flow. But that also may be another another control on the rates of salt flow as well.
Yeah. Well, you have a whole other paper on that.
Yeah.
So I'm making you free publicity right now. So.
Yeah. Yeah.
So
get in touch.
So the last one from the Q&A is Q&A. So it's from Jafar Hassanpour. Actually, it's appearing. So there are some others. I don't know what's going on. So from Jafar Hassanpour, nice work and nice presentation. Congratulations. What is the possible reason for the absence of salt diapirs, except these minor reactive ones you showed in the uptake? Is the system with a thick salt layer?
Yeah, that is a really good question. And yeah, I've thought about that a little bit. The thing is, yeah, a lot of these faults forming in the updip domain for most of the margin are mostly these basinward dipping faults. So we're not getting any kind of the inward dipping faults that you would start to then thin the overburden and generate that reactive rise. But what I kind of thought maybe playing an impact comes back to the intrasalt heterogeneity story as well, because if we have a lot of heterogeneity within those salt units, and if they are less mobile layers within those salt units, maybe that's preventing the kind of vertical movement that you would need to start generating that reactive rise. So if the vertical movement is inhibited by the intrasalt heterogeneity, then maybe you're just getting more of a dominant lateral movement of the overburden on these salt-detached faults. And maybe in the area where we do then see the diapirs, those reactive diapirs in that very localized region of the margin, maybe we're then dealing with an area where the salt is much purer due to the depositional distribution of those intrasalt units. And that could potentially be allowing more vertical movements and allowing more rise from the salt to flow into the accommodation created as those as the overburden is stretched. But that's just a completely out of my brain idea, which needs a lot of testing. So yeah, we're not really sure why one part of the margin is showing reactive rise and the rest of it is just basinward dipping normal faults. Just different ways of expressing tension.
It is an interesting question. It's a good point from him. I think the other thing that you see a lot of contraction in the intrasalts, and then you don't see any contraction in the overburden. That's a bit of an intriguing point as well.
Yeah, I think that's largely related to this thin depositional phase of flow, which I didn't touch on here. There's a lot of literature. Most people that have studied the Messinian have gone and investigated this depositional phase of flow. So there's a lot on that.
Yeah, cool. I think we can wrap it up. Let me see if I can. Well, the last question from the Q&A, and I think you can let you take a break and rest and go enjoy some nice sunshine in UK. I don't know if there's. Yes. I also got some comments saying that you have a very lovely kitchen in my WhatsApp group.
I wish it was my kitchen. I'm actually at my parents' house. It's my parents' kitchen. So.
Right. Okay. That's why. Okay. So yeah, just the last question, and we can probably wrap it up. So from Fadi, I think Fadi had. Hi, Sian. Excellent presentation. Thanks a lot. And well, that's a kind of more outside of scope question. How did salt giant peeps from the European Union help you develop your interpretation? So yeah.
I'm not. Who said that? Was this Fado?
I think so, Fado.
Okay. Oh yeah.
I pronounced wrong the name, but yeah, that's it.
Trying to claim credit to my work. I think that's what's happening here. I've been on a few trips with the salt giant. Well, Leo, you would know because you're around in the basins group. But yeah, been on a few trips with the salt giant European Union funded stuff. Saw the Messinian in person. Went to the amazing Sicilian salt mine, which is why I always post on Twitter if I want to post a cool picture of salt. So yeah, very, very helpful in helping me understand the Messinian salt tectonic. So yeah, all credit to you guys.
Cool. Yeah, I think we can send you the remaining questions. And so, yeah, thanks again, Sian. It was an amazing talk, an amazing topic, very beautiful data, amazing, impressive work.
Thank you for having me. I look forward to the rest of the talks in the series. Thank you, guys.
And the best of luck with your PhD defense. And I'm sure it's going to be a blast. It's going to be a walk in the park.
I hope so.
Yeah. So yeah, thank you everyone for joining the webinar today. I hope you all enjoyed, and that's it.
Okay, yeah, and do get in touch with me if I haven't answered any of your questions. Okay, thank you. Bye.
Bye everyone.
Thank you. That was great.
Bye. Thanks.
Bye.